Welcome, welcome to Finite Element Methods. Today we'll be covering the speaker series, and today we'll be having Dr. Ivatury Raju, and he'll be talking to us about the lessons learned in the application of finite elements in aerospace structures. He's a retired NASA Tech Fellow, and he brings a lot of experience into how to really use finite elements in a sensical way. You will see a lot of the things that he's done are related to fracture mechanics. You will see a lot of the work he's done, and a lot of software use his formulations. In aircraft design, we need to really determine ways of analyzing aircraft. We have to make sure that those structures can experience the stresses and strains in a way that doesn't fail the aircraft. And to do that, we need to learn how to really use finite elements. This is not just for aircraft, applies for aerospace applications as well, like launch vehicles, spacecraft, and things like that. So I'm going to introduce Dr. Raju, who has been working in the fields of fracture and structural mechanics at the Langley Research Center since 1975. And in 1984, he was selected as a branch head of the mechanics and materials branch in the materials division. He has been engaged in extensive amount of work across the industry, especially in the work of durability and damage tolerance. He's been involved in computational mechanics approaches for uh, damage tolerance, and he also has developed accurate methods for the analysis of fracture mechanics. In 2002, he was selected as a senior technologist in SMC, and during the past 20 years, he participated in 4 field investigations, and he's completed a number of them in the past. Dr. Raju has a BS degree in mechanical engineering, a master's degree and PhD degrees in aeronautical structures. And in 2000, Dr. Raju, on a NASA fellowship, attended a program at Harvard University. Dr. Raju is a fellow of the AIAA, and he's a retired NASA Tech Fellow. With that said, I'm going to introduce you, or I'm going to have Raju go through some lessons learned that we can really learn about. So thank you, Raju, for coming over here, and I'm honored to have you here. And I think the students will learn a lot from you. Appreciate it, Raju.
Thank you, Vinay, Dr. Goyal. It has been a pleasure to talk to your class last time, and this is the second time I'm doing. It's really fun to talk to young people, which I always like to do, to give whatever little I know back to the young people so they can ask questions. And so I will just briefly, I won't go through details of this presentation, which I gave in SciTech conference in 2015, but I will highlight the points which I want to make, for you to pick up. And please stop me whenever you feel I have skimmed over something. I'll also give you an opportunity at the end to ask questions. Okay, how do I go to the next chart? I just click. How do I go to the next chart? Okay, here. Yeah, if you see, we have made significant advances in modeling and simulation in the past, since when I was a grad student, let's say. That was a long time ago. And we have got new finite element softwares and tools. We have got very powerful computers. We used to have extremely slow computers without any graphics. Now we have all of those things. All these advancements and improvements are providing us with enormous amount of opportunities to develop complex finite element models and interrogate the designs rapidly and accurately. So we must be able to build structures which are very efficient. Okay. Next chart. Okay, here are the simple, some of the complex finite element models. Next chart. Another view of the complex finite element models. And if you look at the skills, what people have, many of the earlier career engineers like all of you guys are very proficient in using, you grew up with modern computers. We didn't. When we were kids, there were no computers. Okay, now we have excellent graphics facilities that are available. So meshing complex 3D configurations are very simple for you. And you are building sophisticated models very quickly. It used to take for us months to build models which you are saying, which you can do it in a day now. And now you have post-processing and visualization of the results after the results are obtained. These advancements in computing engines are allowing users to have little background. This is the problem which I find very irritating. They have little background in engineering mechanics, and these people are doing performing finite element analysis. We are seeing blind acceptance of the results as the results come out of the computer. Next chart, please. Okay, so these are some of the questions which are posted on the ResearchGate, which I found to be very irritating. Some person asked the question, what is the difference between essential boundary conditions and natural boundary conditions? They should have known that when they learned the Rayleigh-Ridge method, which the finite element method is based on. And some guy asked, what is shear locking? And why do you always use and plot one basis stresses in finite element analysis? I thought these questions were stupid. These questions were asked by people who didn't have any background in engineering mechanics. Next one, please. Okay, so the current trends are there is general lack of understanding of basic assumptions in engineering mechanics. Black box software packages are being used without engineering knowledge. The use of building block approaches in finite element analysis are very rare, which is very, very irritating for me. A well thought out plan to modeling and analysis is rarely evident. They just put lots of elements, millions of elements, and ask the question, why am I not getting the answer? I have seen a result. One of my NASA colleagues from other centers, one of the younger colleagues presents a model where below the fixed line, he had about 7,000-8,000 elements. I said, for what do you have all these elements? You could have just prescribed the fixed boundary conditions of all the nodes which are on that line. And he didn't have an answer to that. Okay, next. Next chart. So the meshing requires, there is this issue on meshing and modeling. Meshing requires expertise in using the software packages, while modeling expertise involves idealization of the structure and understanding the structural response to loads and restraints. So the modeling involves a lot of knowledge on what are you expecting out of the answer. And meshing, if you do meshing just like this young man did, it is just that you didn't know what you're doing. Okay, next one, please. Next chart. I'll skip this chart. These are all details on this. Okay, next chart, please. Okay, the current trends are the 3D mesh models are currently more common than plate shell models. The theme appears to be, when in doubt, use 3D models. Often the solid modeling from Pro-E and SolidWorks are used to develop the shape configuration, which could be good, which could be bad, because you need to prescribe the proper boundary conditions. Most of the time, the people have trouble in the boundary conditions. So let's skip this chart. Go to next chart. Here is what we used to do in the global local mesh with transitions. Here, the current trend is to do a local region with fine mesh and global region with mesh. Now the problem comes, what are you going to do at the interfaces? Okay, people don't think too much about the interfaces, but that interface is is the one that's going to dump the load from this end to the interior. Okay, next chart, please. Here are the global local models of a tailplane. We actually did this for one of the aircraft accidents. We performed the vertical fin, and where the fin, where the vertical tail is joined to the tail cone. We modeled that with local Abacus 3D model. Elsewhere, it is the Nastran model, and we connected both the models and performed the analysis. This is one of the American Airlines 587 accident, which happened in New York City. That's where we had this, the tail fell off, and so we did perform the analysis. I have an AWA paper on this. Next one, please. Okay, I'll skip the details of this global local modeling. Go to the next one. Skip. Next one. Yeah, here is the issue of stress concentrations and singularities in composite structures. There are various places where all of these things occur, and you have to pay attention to those things when you do the modeling. Next one, please.
I do have a question, Raju.
Yeah, go ahead.
These areas are very difficult to understand the results from the analysis perspective. The model can produce results here, but sometimes it's unclear how to use the model to predict failure. Do you have any insights on how somebody that's a young engineer working on this kind of problem can even use the stresses for in any way?
Predicting failure, yeah. Performing the analysis to calculate the stresses is one story. And after that, the next story starts. How are you going to use these stresses to be able to predict failure, as Dr. Goyal asked? That still is an art form which you have to learn from the senior guys who are working this. And my advice to all of you is, when you go into the real world and work these problems, ask the question to the senior guys. What are we going to do about it now? Now we got the stresses. Now what? We apply a von Mises criterion. We apply the maximum stress criterion. We apply the maximum strain criterion. What are we going to apply to be able to predict failure? Predicting failure is a different story after you perform the analysis. Okay, we will see what happens when we get there. Here are some of the current trends which I just summarized here. I don't want to go into all the details. Bolts and bolt modeling is one of the most widely differing modeling techniques that are used everywhere in the analysis domains. Okay, simple smearing of the thickness is done, introducing discrete constraints from where the bolt is, using a beam element and a fastener. I probably have a chart which shows that. Include fastener as one of the more beam elements. A detailed 3D modeling of the bolt head, bolt shrank, washer, including the contact and friction, which is very complicated. You can do that. And you have linear and nonlinear analysis, etc. Go to the next one. Okay, there is in general purpose programs like Nastran, there are special considerations given to special analysis like inertial relief, where you have a spacecraft which is taking off. Okay, when it is taking off, there is an inertial force which is acting on the structure. It is that mx2 dot term which is acting on the structure. Okay, and that happens to be a body force, which is very complicated to model in finite element analysis. So what they did is the Nastran guys came up with an analysis situation called inertial relief. Okay, I didn't know about this. Honestly, I can tell you, I didn't know about the inertial relief because I never worked with Nastran. And I was reviewing one report where for NESC, where one of the teams used inertial relief. And I looked at their plot of the displacements. The whole spacecraft was moving by several inches. The displacements were, they did a contour plot of the displacement. It was shown as several inches. So my question was, as a reviewer, how can a spacecraft have a displacement deformation in terms of 6 or 7 inches? Would it not hit the cone on the top of the rocket? And then what happens? And the analysts constantly complain to me, saying that I'm being a paranoid situation. Then I said, show me how you did the analysis. So they actually give me the reference of inertial relief, which is a Nastran knob which you can turn in Nastran that they can use to be able to simulate inertial relief. Therefore, I went through the theory behind all of that, and said this theory says it needs to be, you need to have proper boundary conditions to make sure that it does not have a rigid body motion. Where have you nailed down the structure against rigid body motion? That was my argument of that. And so we went on this hosing contest for for several days. And finally they agreed that they screwed up. They should have had a few nodes where the boundary conditions should be prescribed to be 0, the displacement to be prescribed 0, and every other displacement is relative to this displacement. And therefore, situations like this would happen where you have rigid body motions, and most of the time, this general purpose program guys, what they are doing is they will hide it because they don't want to get a bad name on their software, saying that every time I run this software crashes. They don't want to get that. Okay, so they actually are hiding the actual truth. The whole idea is they should have told you in their manual, saying that you have to have proper boundary conditions. Anyway, that's the story about this inertial relief. Go to the next chart, please. Next one. Okay, and we all I'm trying to say here is you have to verify and validate your finite element models. The verification and validation are totally two different things. Verification means it is the process of determining that a computational model accurately represents the underlying mathematical model and its solution. That means once you make a model, it actually represents exactly like what the actual structure looks like. And you should also, if you put a load on it, it should get the exact displacement as a continuum solution would give you. That means if you have a cantilever with an end load, your finite element solution should give you the end displacement as PL cubed over 3I. P is the load and L is the length of the cantilever and EI is the flexural rigidity. Okay, that's what verification means. That it means it will exactly reproduce the exact solutions, and it will give you the same answer as what the other methods would give you. If you use finite differences, if you use boundary elements, they'll give you the same answer. That's what it says, verification says. On the other hand, the model validation means it is the process of determining the degree to which the model is an accurate representation of real world from the perspective of intended use of the model. That means if you test a cantilever with an end load and you measure the deflection will be PL cubed over 3I, and that's what this model gives you. That's what model validation is. The model also gives you the same answer as the real test which you are doing. So these are two different things, but your model should actually give you the same answer in verification and validation. So that's what, these are all the definitions given by AAA, ASME, and DOD. Okay, next one, please. And there's a whole lot of literature on verification and validation. This is not simple. This is very complicated. And I borrowed Ben Thacker's chart from Southwest Research Institute in an SAE paper. And this is what this is. Okay, next chart, please. So guidelines and suggestions for all the analysts, like what you guys are trying to become. Most finite element packages have element distortion checks, okay, and will warn the user if the elements exceed certain limits. Limits are subjective, and the bad elements might not give erroneous results, and good elements might be accurate. Okay, my suggestion to all of you is, when you make a model, check the element normals. All normals need to point in the same direction to ensure proper nodal numbering. Use shrink plots to check the connectivity and missing elements. And apply a dummy load which will exercise the components of the model, such as inertial loads. Solve and then validate, and then view the displacement to check for mechanisms and spurious constraints and the like. Most of the general purpose programs will not abort you when you have a rigid body motion, just like what I have discussed previously. They will not abort you because they get a bad name, saying that every time I run this, it bombs. Nobody wants to use a software like that. But the issue is, it is your problem. Your boundary conditions are incorrect. Okay? So you need to pay attention to that. And add density and perform free modal analysis. If more than 6 in 3 dimensions degrees of freedom are there, the model most likely has mechanisms. So there are only 6 degrees of freedom on a free 3D structure. You need to have 6 zero eigenvalues. If you have more than that, then you have a mechanism. Right? Next chart, please. In 2 dimensions, we have 3. A simple, necessary, but sufficient test is to check for geometric nonlinearity, is to impose a full load and solve the problem as a nonlinear system. This is extreme, okay? Most of the time, you don't need to do this. But keep in mind, as an extreme, you may have to do this. And what I would suggest is, for all of you, once you get to a place where you're employed, in the first few years, keep your own repository of elements. If you are going to work in this field, keep your repository of elements. It is your bank of elements, so to speak. Instead of relying on the documentation from your favorite software tool, either it's Nastran or Abacus or Access, develop your own database. Play with the elements and develop your own intuition. Look for McNeil-Harder problems. There is a paper by McNeil and Jim Harder. McNeil is the guy who actually built the first trans-strand situation. He passed away 2 years ago. He wrote a very nice paper on McNeil-Harder, both of them. I think I gave that to Professor Goyal. You can look up, and otherwise I can send it to you. McNeil-Harder a paper. I think it is in International Journal of Numerical Methods in Engineering. It's a very beautiful paper. So you should actually play with them and develop your own intuition on how the elements behave. Okay, next chart.
Hey, Raju, I want to make a point
Yeah.
about this slide. Some students had a homework, a project, and they're getting 6 rigid modes. Basically, six frequencies are close to 0.
Right.
And they're asking why is that? And that's because the model was not sufficiently restrained for that particular problem. So you could do an analysis that's free on purpose. But you could
Yes.
also do an analysis that's fixed with the correct boundary conditions to understand the model frequencies, right?
Yes, yes. Now, in two dimensions, you will have three rigid body motions. The rigid body motions, you can't see me, but rigid body motions are translation along x, y, and is a rotation. Those are the three rigid body motions in two dimensions. In three dimensions, there are six. There are three translations and three rotations about the three axes. Now, when you do a free analysis, I'll tell you a story at this time. Here is a senior researcher. Okay, this was 15, 20 years ago. At that time, we were using what is known as a Comet. I don't know whether you know Comet. It's a software that is developed at Langley, and they are testing it out. And this, at that time, I was a contractor, and he's a colleague of mine, and he's senior to me. He would come and complain totally. He was complaining to me for the last 4 days, saying that Comet, that was the software is called Comet. Comet is something is wrong with Comet. My program always is bombing. It aborts me. So I asked, what the hell is going on, Charlie? and he said, I'm doing this problem for one of the contracts, and I'm doing a free analysis of this beam, and I'm doing the eigenvalue analysis, and it aborts me, saying that the matrix is singular. I knew exactly what was going on, okay? But I didn't want to tell him because he's senior to me and it will like slap on his face, okay? He is using k minus omega squared m, that is equal to a null vector, right? You are looking for the eigenvalues of k minus omega squared m. K is a stiffness matrix, and the stiffness matrix of a free structure is singular. And it is singular of the order of the eigenvalues which you have, or the rigid body motions which you have. There are 6 of them in 3 dimensions, in 3 dimensions, and 3 in 2 dimensions. Okay, so there is no way you can get an eigenvalue answer if you do k minus omega squared m and look for the eigenvalues of k minus 1 m. That's what he's trying to do. Inverse of k times m. That's what he's trying to do. And I'm telling you, in the graduate school, they will tell you, if you want to do a free beam, you cannot do k minus omega squared m because k is singular. You have to do m minus 1k because mass is never singular. You can always invert the mass matrix. M minus 1k, find the eigenvalues of that and take the reciprocals, and you will get to the eigenvalues of k minus 1m. There will be 0 eigenvalues. Okay, so that's what happens when you do not know what the machine is doing or what the theory behind it is. You will say that the software is aborting you. Okay, next chart. So much about that. Yeah, skip this. Is all the bolt modeling also I don't want to skip. Next 2 charts also, I think I can skip next 2 charts. Yeah, these are all details of the bolt modeling, and these are shell 3D analysis strategies. Skip.
This one I want to, if you don't mind, really quick. There are cases which is convenient to have a shell model connected to a solid model, right? Yeah. And so this shows how you could do that. Abacus now has an automated capability that allows for this kind of modeling. It's called shell to solid coupling. So check it out if you're working on a project. This can actually save computational time. So something to keep in mind.
These are some of the stiffeners. This is where you use all of these techniques. So here is a suggestions for mentors and senior engineers. So in this, what I'm preaching is you have to teach hand calculations to the young people, so that they can check their finite element results by using a hand calculation. Most of us don't do hand calculations anymore. Use classical methods to perform hand calculations. If you have a cantilever beam with an end load, you must say the deflection is PL cubed over 3I. Or if you have a simply supported beam with a central concentrated load, you should say PL cubed over 40 IDI. That should be your answer, your maximum deflection. You should know this by like the back of your hand and use these calculations to verify your finite element results. Invest time in developing these skills. Okay, you have to have good strength of materials, good advanced strength of materials, theory of elasticity, plates and shells. And you have to demonstrate and develop skills for evaluating finite element results. That's an art which you can develop. Okay, mentor your junior colleagues and teach best practice skills and teach the tricks of the trade, of the analysis trade. You know, these are some things which you can learn over the period of years. Once you get an output, your fundamental question should be, this finite element solution is wrong. This, whatever I did is wrong. You have to go and prove that what you got is actually a very good solution. You have to go through the process and demonstrate that you have a good solution. Next one, please. Okay, this is simply a summary. Let's go to the next next presentation. Okay, I'll come back to that. Let me go to the next presentation.
So this is the one that talks about the lessons learned, Raju.
Yeah, this is the last chart which I will get back to you after I do the next presentation. There is another presentation, right? Small, yeah.
So Raju, go ahead.
Okay, these are some of the lessons learned. Don't be confused on how to run a code with knowing what the code does. That means if you can run something on Nastran or Abacus or whatever, don't assume that you know what the code is doing. Okay, bigger is not always better. Be sure your results make common sense. Just because it runs to completion does not mean it is correct. Okay, just because the run is completed, it's correct. Don't miss the obvious, even if it is not your job. If something is really, you see that something is wrong with the model, go tell somebody who is responsible to have developed the model, saying that doesn't make any sense. Your boundary conditions do not make any sense, etc. If you think that that's what's going on. Little things are important. The sum of trivia is not trivial. Okay, so a lot of these things look abstract for you, but as you go in your career, you will see that you will hit these things very often. One size does not fit all. Anticipate on how to use different models. And a whole lot of times, as I said previously, if there is a fixed boundary condition, you don't need to put 6,000 elements there and put Young's modulus to be a very large number. It's not worth it. You can just fix the degree of freedom and say, and prescribe those displacements to 0. Okay, understand the sensitivity of your models and the results to parametric variations and the problem uncertainties. This is the most important thing. Most of the time, we don't understand what are the issues in the model. Once you change a small part here, what is it doing to the general problem? Test cases do not always tell the full story. A lot of these test cases you would have run and said, okay, every time I run a test case, my model gives the correct answer, and therefore everything is correct. Okay, know what you do not do, what you do know, understand what you do not know. That is the most important thing. Most of us really don't do this, don't understand it. Things come back around. Plan your analysis and document your process and results. And one advice I want to give you is don't throw away your results. 2 years from now, somebody will ask the question, you did the analysis. What can we see the analysis? There is something else going on here. which we don't understand. We want to review what happened to that analysis. So don't throw away anything what you have done. And finally, be the harshest critic to your own simulations. If you don't believe them, why should anybody else? Your null hypothesis, once you finish the analysis, is your null hypothesis is that this answer is wrong. Okay, you have to go and prove that your hypothesis is wrong, that this answer is in fact correct because of the following reasons. Okay, you must be able to argue that convincingly against anybody. Okay, next chapter. Okay, guidelines and suggestions. Most finite element packages have element distortion checks and will warn the user if the element exceeds these limits. Check the element normals. All element normals need to point in the same directions to ensure proper nodal numbering. Use shrink plots to check connectivity and missing elements. You can do all of this very quickly these days. Apply a dummy load which will exercise all components of the model. Add density and perform a free model analysis. Impose the full load and solve the problem as a nonlinear system. Should get the same answer. Develop your own repository of element test cases, a suite of example problems for your applications. This is what I would suggest that you should do once you settle down in a job someplace. You have to develop your own test cases of elements, and you have to have favorite elements which will give you always a good answer, or you have to develop a confidence in those elements. Look at McNeil Harder paper, which will tell you all kinds of things which can go wrong in that. It's a very beautiful paper. Okay, can I have the next one, please? More observations. We have made significant advancements in modeling and simulation. Okay, new finite element software tools and very powerful computers. All these advancements and improvements are providing us with opportunities to develop very complex finite element models and interrogate their design rapidly and accurately. What would have taken for us maybe 3 or 4 months 20 years ago, you can do all of that in a couple of days now. Okay, and many of you career engineers or career early engineers, young engineers are very proficient in using these current softwares. But the major problem is you are not very good at the background, at the background theory. You have to develop the theory also while you develop the skills for using finite element analysis. Using modern computers, meshing complex 3D configurations, building sophisticated models very quickly, and visualizing of the results is what you are very good at these days. But you should also be good at what the answer you expect out of a problem. You know, that will come from knowing how the structure behaves, for how the analysis, what are the exact solutions, what is an exact solution. However, there's a blind acceptance of the results and issues relative to the quality and interpretation of the results. You have to do, a lot of times you have to make sure that the global equilibrium checks are there. And once you put a load, the displacement under the load is the maximum. That's where it should be, unless you are working a cantilever with a middle load someplace. There are only very few exceptions where the displacements are much larger than where the load is applied. So you have to keep track of all of that. Most of the pitfalls are observed in arriving at proper boundary conditions and interface conditions in the regions of plate shell interfaces, singularities, and the connector modeling, which is all of these interface modeling, regions of plate shell interfaces, where there are stress singularities, and connector modeling. These are the issues where you need to pay special attention to. That's where all the problems are there. improper use of primary and secondary variable results in linear and nonlinear analysis, and inertial relief methods are also frequently observed. Okay, next chart, please. Or is the last one? Summary and recommendations. Yeah. Analysts need to study software developers' manuals. You should actually look at them, NASRAN manual or Abacus manual or ANSYS manual, and and actively pursue verification and validation of their finite element models. They would have told you, this is the problem I'm working, and this is my model. These are the answers which my software gave, and you should actually reproduce what all they did. For each one of you should do that to make sure that you understand what's going on, and experiment with various elements to develop your own library of elements and element report cards in your hip pocket, so that you can pull out and say, hey, this is what we did, and this is the reason why my analysis is correct. Analysts need to be their own worst critic. Once the output comes, okay, your null hypothesis is this is wrong. What analysis I did is wrong. You have to go and prove that your null hypothesis is wrong, that you have actually did all the analysis exactly as what it should be, and therefore your answer is correct. And generate results to support the assumptions and conclusions, not arm-waving arguments and explanations. Okay? Senior engineers and educators need to ensure that the junior engineers receive proper grounding in the classical methods, which is not going to happen these days. And the finite element theory, not going to happen these days unless Professor Goyal teaches you the finite element theory. And simple yet bounding models, hand calculation techniques. You should have hand calculation techniques and methods for evaluating finite element results. This item is most important in my opinion. Senior engineers and educators need to ensure that junior engineers receive proper grounding. You should know what the solution should be. And before you open your output and see the finite element result. The finite element is simply they'll tell you all the numbers, but they are just numbers. Okay, while you have the knowledge of how the structure is behaving, and that's what this item says that you should learn, and you can learn this very quickly in a couple of years. By constant practice, you will be able to do this. Senior engineers need to invest time in mentoring junior engineers. This is very important. And they teach best practices. What are the best practices? Just like what I'm talking about. Teach the tricks of the trade, of this analysis trade. Teach them the processes to evaluate their finite element results before they can accept them. Your null hypothesis always should be, my analysis is wrong. You should go and prove that your null hypothesis is wrong, and therefore your solution is in fact correct. Okay. Is there another chart? Okay. These are some of the general recommendations and from my experience. All analysis and tests are limited and are models of approximations to real life, and therefore they could be wrong because of the approximations you are making. Individual opinions and beliefs need rationale and data. At NESC, we will always say, well, that is your opinion. Bring the data. Or we say we actually believe in God, and all others, please bring data. So that is our principle. So if you want me to believe your answer, bring the data and show me, here is the model and here is what I did for the analysis, and this is what I got, and therefore this is correct. Okay, once you give me your analysis, I will simply say I will trust you, but I want to verify it myself. Then a lot of people asked me, "You don't believe me?" I said, "I don't believe myself. How do I believe you?" When I do an analysis, I feel that I have to go verify it. I don't know if I if I screwed up the day my input. I want to check everything right from the start and make sure that all the output which I got is correct, and therefore I will trust what I got. So if I am doing that to myself, why should I believe what you say? I will go through a fine tooth comb and tell you that this will we will I will work on it. Okay, test. There used to be a wise owl from NASA Marshall called Bob Ryan. He's an old man. He passed away about 2 3 years ago. He used to say, "Test now or test later, but you will test." that's his that's his quote. So that's why I put in quote: "Test now or test later, but you will test." Okay, a lot of times we think that physics does not apply to us, that we are exempt from physics, which is not true. If you're a big program manager, you cannot exceed certain limits because the physics rules, and you cannot change physics. Reality cannot be ignored. You remember that in your brain. Okay, your analysis should verify all anomalies, and before you do verification, you question all the anomalies, and you're doing the analysis to be able to answer these questions and verify that all the anomalies are explained by your analysis. Finally, you have to recognize that all failure scenarios may not be known. When we do a big finite element analysis, all the failure analyses are not known. You are making a model which is a representation of reality. Okay, that's not reality, but it's a representation of reality. We are trying to do the best we can to be able to represent the reality, and we are trying to find out what is the failure scenario which can occur, and that's we are hoping that we have covered all the failure scenarios. And I can give you example after example where we missed the failure scenario and we got caught on it many times.
Yeah,
Expect surprises.
so I do have a question when you said test now or test later, but you
Yeah,
test. I think that's referring to the fact that sometimes it's possible an analysis is developed, but perhaps because of budget constraints, you may not want to do the test, but maybe you end up doing it anyway because you need to check the analysis. Is that what that's referring to?
yeah, but that was referring to what Bob Ryan's experience is. A lot of times the program managers don't want to test because it costs too much money, right? It costs too much money. So, so they will say, "Oh, we don't want to test. We did all this analysis. We did this. We did that," and everybody sits around the table and say, convinces the program manager to do away with the test, and then you have a failure in the real life. Because you did not do the test, you assume certain things are going to happen, certain things are not going to happen. You didn't forecast the actual behavior, and you're not caught on it. How many times it happened to us? Many times it happened to us. This one is a foam hitting the wing is the classic example of when the test was not performed, right? And they said foam cannot hurt us. What do you mean foam cannot hurt us? Did you do the test?
Are you talking the foam, the Columbia?
The Columbia accident. Did the foam? Did you do the test? Did you fire the foam at 500 miles an hour? We didn't, and we got caught on it. Many times it happens. You don't do the test, you get caught on it.
So just for those that don't know, a piece of the external tank,
Yeah,
foam came
foam.
came you broke apart and then
Yeah,
hit the leading edge.
hit the leading edge around that curve there. In one of the panels, the panel 8 or so, panels 8 and 9, and it punched a hole. The foam cannot hurt us. He said foam is like cotton. It has no mass. Of course, it has no mass, but it has enormous amount of velocity, like 600 miles an hour. So you have got this m times v, as large momentum is there. That momentum comes and hit the a flimsy leading edge panel, and then it punched a hole right through that. That's what happened. And that failure scenario was not forecasted.
Right. Because and they didn't test, but they eventually
They
tested.
didn't test.
Yeah.
They did not test. Our foam cannot hurt us. That is the argument we great NASA guys gave. Okay, we are all responsible for each one of us, but we were all headstrong and said foam cannot hurt us. How can a piece of cotton come and punch a hole in a wing leading edge? You forgot that there is a mass and a momentum. There's a mass and a velocity. The rate of change of velocity is acceleration. Mass times acceleration is force.
Yeah, that makes sense. So here's your final chart.
That's my final chart.
It just says
Force is
here.
always with you.
Yeah, the force is always with you. This always makes
Force
sense.
is always with you. Tap into it. Yeah.
Good. Very nice. Well, I mean, we can take questions now. Thank you, Raju, for giving an
Most
excellent
welcome.
presentation.